welcome to RF transfer design course. We are discussing the noise in RF system, module 2. Up to now we already have discussed what are the type of noise sources that are available and some of the important noise source as far as electronics or RF design is concerned. Thermal noise we have studied more in detail. Some light on spot noise is also given. Burst noise also we have discussed, and in the last class we try to uh, find out the noise figure or how noise figure is important, and how noise figure different cascaded system has the final noise figure that we will get the performance of complete system. If there are multiple modules are connected, then how to find the noise figure, that also we have seen. So, in the last class we have discussed that if there is a two component which are cascaded, then output noise power is given by j k t naught b into j1 k t e1 b, and similarly n naught is combination of n1 and the te2. So, then we try to find out that if there is a single component, what is a cascaded noise figure, the noise temperature. So, first we find out T cascaded, which is equal to Te1 plus 1 by G1 Te2. So, finally we come to the equation which is, this is Te1 F cascade, which is equal to F1 plus F2 minus 1 by G1, and if we try to go further, this is a F1 plus F2 minus 1 by G1, F3 minus 1 by G1 plus C2. So, this is called a Friis formula of noise figure cascaded system. You can also write the same thing in terms of temperature if you are representing your system in terms of temperature. So, this equation is important because when we are trying to design a receiver, your first component is significantly going to add the noise. So, whenever we try to connect the first component after antenna, we should have a LNA, that is a low noise amplifier, because if you are adding the noise from the first stage itself, then your entire system noise figure will be degraded. So, there are two things that while designing a low noise amplifier we should keep in our mind, that one is a noise figure of the first component F1 and the gain of the first component, that is a G1. So, your gain also should be sufficient enough, so that because it is going to come into the denominator of the second term. So, your gain also should be very high, or sufficient, so that your next component noise performance can be reduced due to this gain. So, this is an important formula for any RF system design, and while finding out the, we will also see the sensitivity in the later on this class, and then we also try to find out that noise figure has a direct implication on the sensitivity of the receiver. Okay. So, there is a passive components also has a noise. So, how passive component that we should consider, because passive component do not have a gain, but it has a insertion loss. So, that insertion loss L, which is equal to 1 by G, which is greater than 1, where G is a gain of the system. Now, when you are considering the insertion loss or passive component, you should consider the loss, and loss we can try to calculate how we can find out the noise figure of passive components. So, let us say there is a one passive device and then some noise source is there. So, how to find the output power? You can find out N naught, which is equal to G KTB plus G into N added. So, here how much noise which is added by the passive devices we want to find out. So, we can write it down, N added means amount of noise which is added, then we can get 1 minus G by G into KTB. So, in this equation we can also write N naught, we can also represent N naught as a KTB. So, when this term is going on other side, that is 1 minus G by G into KTB. So, you can also write 1 by G minus 1 into KTB. So, here 1 by G is nothing but loss of the system. That loss what we have considered insertion loss. If it is a passive device, there is a insertion loss. So, we can also write because that now current there is a change in the temperature. So, we can also write KB L minus 1 into T. So, this is nothing but the temperature which is change, and that is given by the equivalent temperature TE L minus 1 into T. So, this TE L minus 1 into T we will try to put in the noise figure equation, which is F equal to 1 plus TE by T naught, which is given by 1 plus L minus 1 T by T naught. So, here if we try to consider at temperature T naught, let us say this passive device has a, we want to find the noise figure at temperature T naught. So, at T is equal to T naught, what we will get, this F will be written as a 1 plus L minus 1 T naught by T naught. So, this will be cancelled out, you will get a L. So, this is very important equation, that if you are considering any passive device or passive component which has a loss or insertion loss, then its noise factor is equivalent to its loss. So, always try to remember that when for example, if I have a 4 dB attenuator, then this 4 dB attenuator, how much noise figure it has? It should be 4 dB. So, 4 dB attenuator has a noise figure of 4 dB. So, any passive component you will get the noise figure which is equivalent to its loss, and when you want to include in the Friis formula, when you want to try to consider the gain, then gain will be nothing but 1 by L, that you should consider. So, in this derivation what we try to do is, we have taken any passive component and then one noise source is connected. We try to find out the output noise, how much noise is added, and based on equivalent temperature TE we find the noise factor, and at temperature T is equal to T naught, what will be the final noise factor. So, this is a noise factor, it is in absolute term, if you convert into the dB, it is a noise figure that we have already seen in the last class. So, let us try to find out some, we will put whatever we have understood, try to do one example, so that our understanding will be more clear. So, in this example what has been considered, there is a antenna, and that antenna has a low noise amplifier is connected, there is a band pass filter and a mixer. So, this is a receiver chain. When we discuss receiver architecture, various architecture also we will study, but this is a basic heterodyne kind of receiver structure that has a low noise amplifier, filter and mixers. Now, what first we need to do is find the output noise power in dBm. So, we are interested to find the output noise power in dBm and try to do the same with me. So, here also try to consider the characteristics impedance is 50 ohm and your bandwidth is 10 megahertz. So, whenever you want to find out, first you try to divide the gain noise figure and all the component noise figure step by step, and because we want to find the complete noise figure we should use the Friis formula. So, what is the Friis formula is, that is F, this is the first component. So, F A plus then F minus 1 by G A plus F M minus 1 G A into G F. So, this is a formula of the complete noise figure to find out the noise power. So, first try to convert this dB quantity into the absolute quantity. So, you can write 10 dB which is equal to around 10, gain of 10, then F A is, if we convert into the absolute term it will be around 1.58. Now, because this is a loss, you should write the gain as I already told in the last derivation, that gain is nothing but 1 by LF, then you will get the 0.79 and then your FF is nothing but 1 dB which is equal to 1.26. Then there is LM. So, for mixer there is a loss and noise figure is separately given. So, mixer is a special device where the two inputs will be there. There is a RF input and LO input and you will have a IF output. So, its noise figure is given, that is why, and because this is a lossy mixer there is a loss will be added. So, whenever you want to consider the gain it is 1 by LM. So, GM is nothing but minus 3 dB. If you convert it will be around 0.5 and your FM is equal to 2.51. Now, all these value that we have find out, try to keep all these values in this equation. Once you put in this equation, you will roughly get the noise figure. So, if you write down 1.58 plus 1.26 minus 1 by G A, gain is 10 plus 2.51 minus 1, 10 into 0.79, then you will get roughly around 1.8, and if you try to convert in dB it is nothing but 2.55 dB. So, this is a noise factor of the complete system. Now, in this example what is asked, what is the find the output noise power in dBm. So, first you should convert this into the temperature. You can easily convert TE which is equal to F minus 1 T naught, which you can write, if T naught is 290, 1.8 minus 1, it will roughly come around 232 k. And your gain, what is the gain of complete? That is 10 into 0.79 into 0.5, which will be around 3.95. So, we already have seen in the derivation in the last class, if we have a temperature TA is added, if the system has a gain equivalent temperature TE and bandwidth B, then you can write down N naught. So, what is a N naught? N naught is nothing but K TAB plus, and gain will be added G K TAB into G K TEB. So, GKB you can take it out, GKB, that is TA plus TE. Now, what is the antenna temperature? So, antenna temperature is given, and that is around 150 Kelvin. So, you should know, so antenna temperature, that is means what is the input noise power. So, you can directly find out the input noise power based on the temperature. So, your equation GKB TA plus TE, now you put all the points here, you can find out the output noise power. So, this is a way you can use the Friis formula to find the output noise power. Similarly, there is another part of the example is also there. If the minimum output SNR is 20 dB, then what is the input power? So, you can also find out the input power based on the SNR, that is output SNR that is given. So, your SNR, so there is a part B, SNR out is 20 dB. So, what is your SI? Is nothing but output by gain, and you can also write output signal by N naught into N naught by gain. So, as SO by NO you already know. So, 20 dB is given, output power we have calculated using this, you already know the gain, you can find the input power. So, this if you try to find out the input power, it will roughly come in 80 to around 80 to 90 dBm. So, if what it says that if you want a sufficient SNR of 20 dB, then you should have a sufficient input signal, and when we discuss the sensitivity at that time also we will discuss that it is in this example it is coming roughly around minus 80 to minus 90 dBm. So, this example is really help you to understand how you can use the Friis formula to solve the RF receiver system analysis or design. So, we can also have a different types of methods available to find out the noise figure. We already seen the Y factor method. There is one method that is used to find the noise figure, that is called a gain method. So, in gain method what exactly has been done? So, your noise factor, what is the noise factor? That we know SI by NI means SNR in by SNR out. So, if this is SNR in by SNR out, I can also write Si by Ni into No by So. So, in this case, if this is a gain into Si, so I can also write it is N gain into Si, then this will be cancelled out, and you can write it down No into Ni into G. So, here this noise spectre you can also write like what is the total output noise power, what is the total output noise power divided by output noise power due to input source, because here we have just considered input source noise power Ni and the gain is added. So, this is only output noise power due to the input source. So, this by using the gain methods generally we can use a spectrum analyzer to find the total how much power spectral density, output power spectral density we have, and based on that we can get the output noise power due to the input source. So, output noise power due to the input source we can easily find out. Ni is nothing but KT, then noise figure you will get which is equal to P No minus. So, if you try to convert 10 log KT, so that will come around minus 174 dBm per hertz, and because we are considering the with respect to unity bandwidth, it is minus 174, and then you should add the gain. So, this is a noise figure equation. So, if you write it down, rewrite it again, P No plus 174 minus gain. You can also, so what you need to do first, you should know the your device under test what is the gain. So, for finding out this method noise figure by using this method, you should know prior that what is the gain of your amplifier or gain of your system. If you know the gain, then only this method is useful. So, you should know the gain, then once you know the gain, you just try to connect the noise source, means 50 ohm noise source, and then find out the output noise power in power spectral density in spectrum analyzer, and you need to in order to get the accurate analysis as per the design guideline, your resolution bandwidth by video bandwidth should be around 0.3 when you are using a spectrum analyzer. So, if you have a roughly kept around 0.3, you will get the means your noise floor is much below, and your analysis will be accurate. So, for example, if you have a power spectral density output PST you are getting is minus 90 dBm, and then your gain of system is around 80 dB, you can easily put this in this equation and find out the noise figure. So, nowadays there are many equipment are available, means from Keysight. So, using a network analyzer also you can find out the noise figure. So, all these features are added. so that you can easily find out the noise figure using gain method. Y factor method we have already seen, cold and hot source, that method we have already seen, and Y factor method is also simplified somewhere, that is called by using a excess noise ratio. So, excess noise ratio we have already seen what is excess noise ratio in the last class. You can also use this method to find the noise figure. You can use the following equation. So, the equation is y which is equal to by f plus 1. So, how exactly this method, you have an active noise source will be available with you, and that active noise source has a excess noise ratio has been defined. So, you need to find the power when active noise source is on. So, there is a one power when active noise source is off, when active noise source is off, and then you have another power when it is on. Then you will get the y factor which is y, and you are at different frequency. So, if you are purchasing the noise source from any vendor, they will provide you the for different frequency what is the active noise source, and when it is provided, you can find out easily. You have a y is available, you have a excess noise ratio is also available, you can easily find out the noise factor. So, in measurement widely these two techniques are used to find the noise figure of any system or any component. We will try to move to the next part of the course, that is a. So, before going to the linearity, I just want to add few points. So, before going to the linearity, I want to add a few points related to the what are the noise sources in the certain components, and what is the equation for that we will see. So, that is a useful noise calculation. So, if you try to consider the diode. So, first we will start from the diode. So, in diode, in last class I already told what is a dominant noise, that is a short noise, and there is a series resistance also. So, series resistance and then short noise due to the current, direct current flow. We will try to derive the same. So, if this is a diode, if current is flowing, that is ID, we can also model it. There is a series resistance Rs. So, due to series resistance there is a noise that is Vs square, and then there is a Rd resistance Kt by Q into Id, and noise current, that is a short noise, that is I square. So, you can write Vs square which is equal to 4 Kt Rs delta F. So, in many cases if you consider the volt square per hertz power spectral density, it is generally written as a 4 Kt Rs. I square also we can write it down 2 Q It delta F, plus there is a flicker noise also that we should consider, that K into IDA by f into delta f. So, this is a flicker noise, and the flicker noise always, if we try to draw in the log scale, it is inversely proportional to the frequency. So, this is a power spectral density, and if it is a log scale and this is a frequency, it is inversely proportional to the frequency. And in this k is a constant. This constant will change with the devices, constant for device. Then ID is a current, direct current, and f is a frequency, and A is a constant. So, this will vary from 0.2, 0.5 to 0.5 to 2. A constant will vary 0.5 to 2. There is a constant B also. This will be around unity. It might change if you change the process. So, when you consider the diode, because in many RF application diodes are used as a switch, various switches are implemented using diodes. So, if you want to analyze what are the noise which is added, because generally the switches are used where we have already discussed in the wireless communication basics that in TDMA you need to switch. So, when you are trying to implement time division duplexing, you switch from transmitter receiver. At that time, if you are using a diode, because high speed diode is easy to implement, if you try to implement a diode, then you will get all this noise. And what are the dominant noise in this? The dominant noise is a short noise, and due to the series resistance there is a thermal noise. So, we will also discuss all diode. We have already discussed the noise calculation of diode. In the next class we will try to discuss about, so BJT and FET. So, then BJT, FET or MOSFET are widely used component. FET, MOSFET are widely used component in RF system. So, we will also try to analyze the noise of BJT, FET and MOSFET in the next class, and we will start the linearity as well. So, thank you, and we will discuss further more in detail about the noise in FET and MOSFET, BJT and MOSFET. Thank you.